All right, so topic 23, another two-sample procedure, but this is for dependent samples. It's called a matched paired key procedure, or just a paired key procedure. So if you have two samples that are not independent, such as the same set of 12 people doing two different tasks, or like we just did with the chocolate chips and the peanut butter chips, 20 people doing two different tasks, we're going to use a t-test with a single set of data made up the differences between the two sets of data. The key advantage to this is that it reduces variability, and it makes it much easier to detect a difference between the two groups. Right? We were comparing the melting time between peanut butter chips and chocolate chips, right? And we are going to make our conclusion. So I think that for this one, the true mean difference, I think peanut butter chips are going to take longer to melt, right? I got milk chocolate chips, so I think that those will melt faster than peanut butter. So if they have the same melting times, the mean of those differences should be 0, right? Does that make sense? There would be no difference between the two. And if I think peanut butter chips take longer to melt, I think that mean difference should be greater than 0, right? So this is you can say matched paired t-test. And the mean of the differences is the true mean difference in melting times PB minus chocolate chips. And then our conditions down here. Right? So here's always our conditions. And we'll test this with a 5% significance level. Do we have a random sample or a randomized experiment? How could I have issued a randomization in here? Did I tell you specifically whether to choose chocolate or peanut butter first? Would that make a difference? Yeah. So we're going to say simple random sample? No, but randomized experiment. And the set of differences must be greater than 30, or the graph of the differences must be approximately normal. So now it's not 20 plus 20 is 40, which is greater than 30. It's the set of differences. So our sample size is just the number of differences. In this case, we only had 20. So I'm going to go ahead and look at a graphical display. We already said these were dependent samples. All right, so let's look at a graphical display in our calculator. I'm just going to look at what the differences look like. So I'm just going to do that one. And I'm going to do a histogram of the differences. And that's going to be mine are in list 3. And my differences are fairly symmetric. With a couple of small outliers. So it may not be normal. Those ones with extreme differences. So I have from 8 to 16.8. That's 5 in here. 4 in here to 25.6. 9 in here between 0 43.2. And then we had some extreme differences. 52. And then this one was all the way up to 60.8. And 1 in each of those. So our majority is right here. Right? And based on this, I wouldn't necessarily think that there's a lack of normality in the population. If we had just one more sample somewhere in here, it should be fine. So make sure we label this so you can see. Right? PB minus chocolate chip melting time. And then title it histogram of differences. Right, so make sure if you are going to use your calculator, you do label it and just don't put what the TI kicks out. Right, and then we're going to say, based on the histogram, I have no reason to suspect a lack of normality in the differences. It's fairly symmetric. That's all we're looking for. And then we're going to calculate a t-statistic. Okay? This is just your regular t-test like we did from topic 19. Okay? I want my t. My p-value. And I'm going to decide whether I reject or fail to reject. So I'm going to stat. Go over to test, and it's just a t-test, right? Let me put this. So I get my t of 9.68. My p-value is approximately 0. So 0 is less than 0.05. I'm going to reject H naught. And at the 5% significance level, there is sufficient evidence to say that the true mean difference of melting times between peanut butter chips and chocolate chips is greater than 0. It appears peanut butter chips take longer to melt. And I always add this last sentence to make it clear, right? Because when you're talking about the idea of a true mean difference, sometimes it's hard to tell which one's greater than the other. Right? So if I want to figure out the magnitude of the difference, what do you think I do? Our confidence interval, right? We can do our confidence interval, and that's just going to be a key interval. If I do a 95% confidence interval, the conditions are going to be the same. And this will tell me, on average, how much longer it'll take for peanut butter chips to melt than chocolate chips. So this is even more useful than when we're comparing the differences between those, because this gives me a specific interval for the true mean melting time that peanut butter chips take longer than chocolate chips. So I am 95% confident that the true mean difference in melting time is between 19.165 seconds and 29.735 seconds. So we can say that chocolate peanut butter chips take anywhere between 19.165 seconds to 29.735 seconds longer to melt in the mouth than chocolate chips.